Hi, I'm Ariadna Garcia, and the poster titled Photoelectroactivity Evaluation of lanthanum perovskite fibers synthesized by electrospinning is about how we evaluate the photoactivity of the perovskite and if it can be used as a photocathode to catalyze the oxygen reduction reaction. To test the material, we use simply photoelectrochemical techniques as open circuit potential and chronoamperometry to evaluate the photopotential response and the photocurrent response through the time in darkness and under illumination. For all of this, we first obtain membranes applying 15.5 kilovolts voltage between a sandwich and a collector, where we can see here. This while pumping these precursors of the metals in DMF and PVP under the conditions that we can see in the screen. Once the membranes were obtained, we carried out a calcination using a simple furnace at a 700 Celsius temperature during 2 hours to obtain a black powder that was the perovskite, the material perovskite. And then we deposit this powder, perovskite powder, in glassy carbon electrode surface to be evaluated in the setup that we can see here in the screen, where we can see the solar simulator in front of a Faraday cage that has a hole uh, in the Faraday cage to let pass the light through it and irradiate a 3-electrode set with that has a quartz circle window to let pass the light and evaluate the perovskite. The results we obtain are here. We first can see a micrograph taken with an optical microscope where we can observe the threads formed by the sandwich during the electrospinning process. In order to prove that we obtained the perovskite structure, here is a diffractogram of the powder obtained from the here is a diffractogram of the powder that we obtained. And from here we can say that we have an hexagonal perovskite with the stoichiometry that it's here right in the conclusions. According to the the crystallographic cartograph. To evaluate the window potential of the material and to know if it is stable, we apply a cyclic volt amperometry where we can observe there is no reaction peaks, so it is stable in a range of minus 700 millivolts to 1.2 volts versus the reference. And for the photoactivity test, we record the potential of the material through the time, that is this figure, where we can see that the material first will record the open circuit potential, 30 minutes in darkness, then 30 minutes under illumination, and again in darkness. And we can observe that when the light is on, the potential response tends to go to the positive potential that indicates that it is a p-type semiconductor and it can be used as a photocathode. For the photocurrent response evaluation, this was carried out with a chronoamperometry technique where we applied a cathodic potential of minus 700 millivolts versus the reference here in this figure. These response were recorded in darkness under illumination and with chopped light. From the graphs, we observe that when the light is on, it tends to negative currents, and when the light is chopped, we can say that it has a slow reaction with light. not reaction, is more like a slow response when the light is on. So from all of this work, we can conclude that we have an hexagonal perovskite. We can obtain an hexagonal perovskite with this electrospinning method. That and also that this perovskite is stable at a wide range of potential in alkaline medium. This material also presents a typical photoactivity of a p-type semiconductor, and it presents as a slow photocurrent activity when a cathode when a cathodic potential is applied. And I think that with a structure optimization of the lanthanum perovskite, it can be used as a photocathode for the oxygen reduction reaction.